This webcast discusses how to do the qualitative observations portion of the Gravitational Force Lab. In this lab, we are going to use one of the University of Colorado PhET simulation tools, and there is a link provided to this tool at step 1 in the lab. So you should click on this link to open that up. It will take you to this page, and from here you want to play the simulation, and so I'm just going to hit the play button. Okay, and so here is this simulation tool. You can see that we have these two men who are holding on to large spheres, and there are dashed lines which indicate the position of the centers of those large spheres. We have tools down here where we can change the masses of both spheres, and then up at the top of the screen they are telling you the amount of the gravitational force that each mass is exerting on the other mass. And the arrows show the direction of those forces. And so I can see that here, this blue mass 1 is feeling a force of this many newtons that's being exerted by mass 2. And here, mass 2 is feeling a force being exerted on it by mass 1 with this many newtons. Okay. As far as setting up this tool, there are a couple of things that you'll want to do. One is that we would like to make the spheres a constant size. And so I'm going to click this box for constant size. And then the other thing is that you'll notice that this ruler, you can move it around. And so I'm going to move the blue sphere a little bit further to the left, and I'm going to move the ruler so that the 0 meter indication is aligned with the blue dashed line that passes through the center of the blue sphere. Now, when I move the red sphere, I can see, I can read directly off of this meter stick where that red sphere is. So I can tell the distance between the center of the spheres. Okay, so we have it set up, and now let's go look at some of the qualitative observations that we want to look at. Okay, so I'm going down to the second page of the lab, and we have set up the simulation tool, and it says notice that the magnitude of the gravitational forces is very small. Look here, it's 0.00000076692. That's a very small number of newtons. And so we're going to want to write these forces down in scientific notation. And when we do that, we will use the exponent notation, which means that we will put the leading number and then we will follow it with the with an E, and that E is notation that tells us that we're going to then multiply by 10 raised to the power of whatever follows the E. And so this is the same thing as 1.2334 times 10 raised to the negative 8 power. Okay, those are equivalent, but we want to write it in exponent notation because that is what Microsoft Excel will recognize when we put our data in Excel. Okay, but there are a few things we want to just observe about this simulation tool before we start doing our experiment. So first of all, how are we going to read the distances between the centers of the masses? Let's look at that ruler more carefully, count the divisions between, for example, 0 and 1, and understand how much distance is represented by each of those divisions. So if I look here at the tool, I see that there's 1, 2, 3, 4, 5 divisions between each of the numbered meters. And so 1 meter is divided into 5 divisions, and that means that there is 0.2, 1 divided by 5, 0.2 meters per division. Okay, so if we see a distance that is, right now my red sphere, the red dashed line is here at 5.8, right? Because it is 4 divisions past the 5 meter mark. Each of those divisions is 0.2. So here would be 5.2, 5.4, 5.6, 5.8. Okay, so I understand now that each one of those divisions represents 0.2 meters. Okay, let's figure out what is the smallest distance that this simulator will let you set between two 100 kilogram masses. So I'm going to make each of them 100 kilograms. Okay, and then I'm going to move them as close together as I can. And I can see here my 0 dash line is on the 0. My red dash line looks like it's about halfway between the 1 and the first tick mark. Well, that tick mark would be 1.2, and so it must mean that there's a distance of 1.1 meters. That is the closest that I can get those two spheres when they are the same size. Okay? Then I want to try to understand how that force, the gravitational force, changes and how it depends on different factors. So first I'm going to look at how does the force between those two masses change as the distance between them changes. So I'm looking at the effect of distance. And so it says create two masses that each have 100 kilograms. Okay, I've done that. Then it says keeping both masses the same, let's change the distance between them, and then we're going to write down the amount of force. So first I'm going to make the distance, I'm going to pull them so that they are 2 meters apart, and I see I've got these two forces, and look, they're the same numbers, right? I'm going to record that force. Now I want to put it in scientific notation, and so my first number is 1, 2, 3, 4, 5, 6, 7 places to the right of that decimal point. So I'm going to put 1.66852 times 10 to the negative 7th. Okay? Let's look at what the force is when they are 4 meters apart. Okay, now I can see, let's see, my first, I would have to move that decimal place 1, 2, 3, 4, 5, 6, 7, 8 places to the right to put this in scientific notation. And so I would have 4.1713 e to the negative 8. And now I'm going to make the distance 8 meters apart. Okay, so now they are 8 meters apart, and here's my force. Let's see, I'm going to have to shift that decimal place 1, 2, 3, 4, 5, 6, 7, 8 again. So it's going to be 1.0428 times 10 to the negative 8. Okay, so I can tell by looking at these forces that as the distance gets larger, the force is getting smaller. So that's an interesting observation, but I can even do better than that. I can find the specific amount of the change if I look at the ratio. So it says find the ratios, the force at 4 meters divided by the force at 2 meters apart. So let's see here, that would be 4.1713 e to the negative 8 divided by the 1.66852 e to the negative 7. Let's see what we get when we do that division. So 4.1713 e to the negative 8 divided by 1.66852 e to the negative 7. And it is 0.25. And then it also says to look at the ratio of the force at 8 meters divided by the force at 4 meters. You know, I want a couple of data points. Let me see if I get the same ratio when I divide these others. So here I would have 1.0428 e to the negative 8 divided by 4.1713 e to the negative 8. And if I do this math, I'm also going to get 0.25. So then we can say when the distance between the centers of the object doubles, the gravitational force changes by a factor of 0.25. It's, in other words, the force at 8 meters is only 1/4 as large as the force at 4 meters. The force at a distance of 4 meters is only 1/4 as large as the force at a distance of 2 meters. Okay, so by taking those ratios, I'm able to get a more specific answer. Okay, let's see what happens if we change the mass of the object. Okay, so we're going to change the mass of object 1, and that's the only thing we're going to change. So I want to keep my mass of object 2 constant. I think right now I have it set at 100 kilograms. I can leave it at that. I just don't want to change mass 2. So I'm going to leave that at 100 kilograms. And I'm going to leave the distance between them the same. So right now I've got them 8 meters apart. I can just keep them at 8 meters. That's fine. I'm just keeping these two things constant. I'm only going to change the mass of object 1. So let's set that mass of object 1 to 200. Okay, and I'm going to record the force. So let's see, I'm going to have to move the decimal place 3, 6, 8 places. So I'm going to have 10 to the negative 8, and my force is going to be 2.0857 e to the negative 8. And then if I change the mass of object 1 to 400, okay, a little hard to get to 400, but I'm going to get there. There we go. Now I see that I'm still going to have to move the decimal point 3, 6, 7, 8 places to the right, but I've got a little bit more force, so 41713. Okay, and I want to look at the ratio. Okay, so I want to look at the force when mass 1 is 400 kilograms compared to the force when mass 1 is 200 kilograms. That way I'm looking at what happens when I double it. Okay, and so I've got 4.1713 e to the negative 8 divided by 2.0857 e to the negative 8. Let me do that math and let's see what we get. I get a ratio of 2. And so therefore I would write a sentence. The gravitational well, I've spelled it wrong, girls, but we're going to go with that. The gravitational force doubles when the mass of object 1 doubles. Okay. So again, I wrote down my data and then I looked at a ratio. I was looking at when the mass doubled, and so I wanted to put the number where the mass was twice as big on top of my ratio. I did the math. I see that the force is doubled, and then I wrote the sentence. I'm going to leave you to do number 8 on your own. And let's look at one more thing, which is number 9. In any of these situations, did the force on mass 1 ever differ in magnitude from the force on mass 2? Remember, magnitude just means the amount. Well, look here. I mean, I see the same numbers for the forces all the time. Now, the directions are different, right? This force is pointing to the right, this force is pointing to the left, but when I change the distance, the force changes, but they're always the same amount of force. If I change the mass, the magnitude changes, right? But the force on mass 1 is always equal to the force on mass 2. And so I think, no, we never see a situation where the magnitude is different. So the magnitude of the force on mass 1 is always equal to the magnitude of the gravitational force on mass 2. So, no matter what we change in this simulation, those two numbers are always the same numbers. Now, it says, did the two forces ever not point in opposite directions? And I think, no, they always pointed in opposite directions. The force on mass 1 always pointed to the right, and the force on mass 2 always pointed to the left. So they always point in opposite directions, and the magnitudes are the same. So then the question is, which of the models that we studied in first semester might apply to this situation? And I think I remember that Newton's third law says that all forces are created as pairs of forces with the two forces having the same magnitude but opposite directions. And so the gravitational force is also a third law pair. The gravitational force that's being exerted on mass 1 by mass 2 is the same amount but in the opposite direction as the gravitational force being exerted on mass 2 by mass 1.